Hello everyone, I am Michael Holly and today I am presenting an asymmetric multiplayer learning environment for room scale virtual reality and handheld devices. Teaching and learning science, technology, engineering and mathematics are often challenging and time consuming. Getting people engaged in science across STEM disciplines is essential. But for many students, STEM fields are uninteresting, complex and hard to learn. To create an even more engaging, inspiring learning experience, virtual reality technologies can be used to promote motivated usage and high user adoption. In recent years, the use of VR for teaching and learning purposes has been explored. However, the use of collaborative multiplayer elements in VR for learning purposes has not been explored in detail. In this work, we propose an asymmetric VR multiplayer application that is inspired by VR learning environments, multiplayer concepts from video games, and collaborative learning. During the COVID-19 pandemic, students showed a lack of motivation. Therefore, it is important to actively shape the educational experience and consider the way students communicate, interact, and collaborate with each other. Computer-supported collaborative learning are one way to address this generation of learners, considering multiple students working together. A collaborative learning environment typically consists of positive interdependence, meaning that group members rely on one another to complete a task, considerable interaction, where members help and encourage each other, personal responsibility, social skills, and group self-evaluating. To obtain a more immersive, engaging feeling, the potential of virtual reality technologies can be used to develop engaging learning experiences. The advantage in the use of three-dimensional virtual worlds is the positive effect of immersion in learning processes. Virtual laboratories in combination with VR tools give an even more immersive experience. Users are fully immersed in the virtual environment and must handle the situations in a realistic way. Entering the virtual world reduces any distraction caused by external influences. Nowadays, there are several VR laboratories developed and used for training and education scenarios. Teachers identified only one person being immersed as a potential issue if VR is used in a group setting. This can be overcome by drawing inspiration from multiplayer game design, where more than one player is considered. In a similar way to collaborative learning, the concepts of cooperation and interdependence also apply to asymmetric games. The benefits this type of game design brings include allowing players of different skill levels to play together, strengthening teamwork, fostering critical thinking through knowledge asymmetry. To evaluate asymmetric learning in VR, we implemented a framework that supports the creation of an asymmetric VR multiplayer experience. The framework is designed for the Valve Room Scale tracking system using base stations to track the headset, controls, and other trackable devices. In our setup, both users are located in the same room to allow the tracking of all devices via one base station pair. To run the asymmetric VR experience, the following hardware components are required: a gaming PC, two VR base stations for room scale tracking, a VR headset and two corresponding controllers, a tablet with a tracker, and a wireless network router. In order to test and experience the features, we implemented a specific learning use case about digital color and the RGB color model. The tasks given to the users through on-screen instructions are to find the RGB color values based on a given color, then make a pixel light up in the correct color according to these values. The experience requires both users to communicate and work together. To find the RGB colors values, the handheld user needs to compare two colors, while the VR user manipulates one of them using an interactive RGB color cube. The resulting values are then only visible to the VR user, but need to be entered by the handheld user. The focus of this study was on the social presence from the two different perspectives in an asymmetric VR learning environment, as well as on the motivation, learning experience, and outcome. The goal of the study was also to investigate the different levels of dominance between the two asymmetric users and to identify which user feels more in control. To compare the distinct experience, we conducted an A/B split user study with 14 participants. To perform the study, we used a gaming PC with a high-performance graphic for rendering the virtual world and streaming it to the handheld device. For the VR setup, we used an HTC Vive headset, 2 controllers, and an HTC Vive tracker. For the handheld tablet, we used an Android 12 tablet. The setup itself was located in a single room where the participants had a play area of 3 meters times 3 meters. Each group consists of 1 VR user and 1 handheld user. After assigning them to groups, we asked them to fill out a pre-questionnaire. It included several questions about general personal information and prior experience. To assess the learning outcome, we asked the participants the same knowledge question before starting the experiment and also at the end of the experiment. After completing the pre-questionnaire and the knowledge questions, participants were asked to perform the experiment. Both users had to work together to find out the correct RGB value for the color displayed on the tablet. For the measurement, we used several standardized questionnaires. In the Valence domain, most participants had a positive experience when using VR and the handheld device. For the aerosol category, users rated the VR perspective as neutral and the handheld perspective was rated moderately higher. The dominance level was rated almost similar in both groups. The findings indicate that VR users are empathetic when collaborating with handheld users and vice versa. Furthermore, the results indicate that users had no negative emotions towards the other user. The level of behavioral involvement was rather given a relatively high ranking for both user perspectives, with a moderately higher rate for the VR perspective. The PXI results indicated high levels of curiosity, audiovisual appeal, and clarity of goals. Overall, VR users rated the ease of control higher than handheld users. Users differ most significantly on the statement it was easy to know how to perform actions in the experience. The results of the QCM indicate a low level of anxiety for both perspectives and a high probability success and interest. Users rated the challenge level as moderate, and there were no significant differences between the two user perspectives. To evaluate the learning outcome, we asked the participants for knowledge questions before the experiment. 42% of the participants answered the knowledge questions correctly in the pre-questionnaire. After finishing the learning task of the application, 81% of the participants were able to answer the same questions correctly. The test results indicate a significant improvement for the knowledge question regarding the visualization of the RGB color model. In conclusion, the findings suggest that although many people prefer using a VR headset over tablets when entering immersive worlds, there is still interest in traditional forms such as handheld devices. Due to familiarity, users feel more comfortable interacting with tablets than with VR headsets. In general, the participants were satisfied with the learning experience and were also able to improve the knowledge about the learning content. It provides teachers with an additional tool to adequately prepare students across a wide range of topics. Many thanks for your attention.